So this video is going to introduce one of the most common types of research designs used in learning research, even though this isn't a research design that's as well known as those in other fields of psychology. So in something like cognitive psychology, we might do an experiment by bringing 100 people into the lab and randomly assigning them into two groups, an experimental group and a control group. And then we manipulate an independent variable and see how that affects a dependent variable when we average across the whole group of 100. That's how a lot of psychology works, especially in the more experimental branches. And we can learn a lot, even when we limit ourselves to discovering effects that are averaged across big groups. But in the psychology of learning, in the experimental analysis of behavior, we often do what's called single subject research. Now, it's essential to understand when I say that single subject research does not mean that you only study one subject. It doesn't mean a sample size of one. What it means is you collect and analyze data on each subject individually. You don't analyze group averages, you analyze what happened to this subject specifically. And you use experimental design to get evidence of causation to show that this subject changed their behavior due to your intervention, your manipulation. But you can repeat that for a bunch of subjects. You can have a large sample size. And certainly more than just one participant, but you analyze them individually. That's what makes it single subject research. Now, we will discuss a variety of single subject research designs in this course, but the most popular are versions of what we call reversal designs, and that's what this video will cover. So reversal designs are experiments where you're going to switch back and forth between baseline and treatment, or treatments over time. When I say baseline, I just mean we'll first measure how much the target behavior we're interested in, how much it happens without any treatment. So this is our control condition. Then, after you've measured the baseline for a while, then you introduce the treatment. Whether it's a drug you inject, or a training you administer, intervention you do on kids, or letting a rat run through a maze 50 times while Mozart is playing, whatever your independent variable is, that's when you do your manipulation. But then you're going to go back to the baseline condition where the treatment isn't present anymore. Then after a while, you might go back and do the treatment again for a while, and then go back and do another phase of the baseline, and so on. That's why it's called a reversal design. Each time, you're going to measure how much the target behavior happens so you can see whether the treatment causes any change in it. Now, you can do this baseline treatment reversal many times, or just do the flip a few times, depending on how much time you've got and the cost involved and how confident you need to be in your results. So if it's a huge or expensive policy change at a big school, then you may only be able to do the reversal a few times, whereas if you're studying rats in a laboratory, you can maybe do it 10 or 15 times or more. A common way of writing out reversal designs is like ABA, or ABAB, or ABABA, or whatever it is, to signal how many times you did the reversal and the order of those conditions. So in this case, A would be the baseline. It's how you start, right? Since you measure that before you start your treatment. Then each of those B's in the series represents when you did the treatment, a treatment phase, so to speak. And you can see that we interleave, we go back and forth between them. Now, a key point is we don't just measure behavior one time during each baseline phase or one time during each treatment phase. That wouldn't tell us very much. So each stage, each of these phases, will often involve many measurements to get a general picture of the pattern. We might even stay in that phase until we can see a very clear and consistent pattern of behavior. That is, until they've gotten into like a steady state of responding, and then we can switch things up again with a reversal. That means that even for an individual subject, we might have hundreds of data points, or follow that one child for months and months of data collection. So once again, the term single subject design might sound a little misleading if you're picturing a sample size of one, a single data point. But really, we can do lots of participants like this, and also for each participant, we can have tons of data points. So it would still be a single subject design because we're analyzing each subject's data on its own. That's what makes it single subject. And each time, we're going to be looking at things like did the behavior change when the treatment was turned on, and did the behavior go back to normal when you turned back to the baseline condition, when you go back to the A phase? So this is what data might look like for a very simple ABA reversal design. For example, if we've got a kid who's disrupting her second grade class a lot, and we want to study the effectiveness of an intervention such as praising her when she's on task, we might do the study like this. We first spend a few days simply measuring how much she disrupts the class on average as a baseline. Here you can see it's around 6 to 7 times per class. Then we'll institute our treatment, the intervention of having the teacher praise her for being on task. And this whole time in the B phase, while the treatment's active, we're going to keep measuring her disruption behavior and graphing it out for days 4 through 10, for example, here, right? Then during the treatment, we can see she seems to settle to around 3 or 4 disruptions per class instead of 6 or 7. At that point, we might go back to baseline, stop giving praise for being on task, and measure the disruptions for a while. And in this case, you can see they seem to go back up. That's the basic idea of a reversal design. This gives us at least some evidence that the praise intervention might be causing changes in disruptive behavior. In other words, we can use it to determine what interventions work or don't, what factors, what variables change behavior or don't change behavior. That said, the evidence is going to be a lot stronger if we do more reversals. The more reversals you do, the stronger the conclusion, assuming we keep seeing the same thing every time we flip that switch. Basically, the more reversals we do, the more strongly we can rule out coincidence or things like outside events causing those behavior changes. In the previous study, maybe the girl showed less disruption on days 4 through 10 because her cousins were visiting that week, or because her parents tried an all-vegan diet that week, or there's stuff we wouldn't know about. We just can't rule such things out with a simple ABA design. But if we keep doing reversals, AB, 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 and the behavior always goes down when we flip the switch to B and always goes up when we flip the switch back to A, regardless of the time we do it, then we can pretty strongly rule out coincidence and be sure it's our intervention that is the cause of the behavior change. To get a feel for the logic of reversal designs, but also one limitation of reversal designs, consider what our data might look like when we run an ABABA reversal design, a study with that kind of design. If our data looks like the graph up top, the question is, should we conclude that the treatment works? And what if our data looks like the graph in the middle here? Should we conclude that the treatment works? Or what about the data in the bottom? If we see that at the end of our study, should we conclude the treatment works? You can pause the video and think about these for a minute. Think about what you would take as convincing or not, and maybe see if you can come up with alternative explanations. So the top graph, I would say, provides, at least some decent evidence that the treatment works. Obviously, more reversals would strengthen that conclusion a lot, but it at least fits well with the hypothesis that the treatment affects the behavior, and we can rule out some of the biggest confounds like basic coincidence. So I'd say, yeah, we got some evidence maybe that the treatment works, or we can at least start thinking that. In the middle graph, there's really no clear evidence that the treatment worked, right? We might even conclude that the treatment probably doesn't work, at least not in the way we tried it in this study, because everything kind of stays the same, right? Turning on the treatment didn't seem to do anything. But in that bottom one, right, we've got something interesting going on. In the middle one, there's just as much variation within any of these, treatment conditions or phases as there is between any of the two of them. There's no big difference there. In the bottom graph, we do get a change. We get a big change, right? There's not much change, not much variation or not much variability here in this first phase. But by the time we turn on the treatment, we're getting pretty extremely different results that none of these data points is anywhere near the data points we were seeing before. Like that seems like a pretty real change. But we've got a problem. When we go back to baseline, the A condition in the middle here, the behavior stays changed. There are a couple of possible explanations for that, which is a problem. So possibility 1 or explanation 1 would be maybe the treatment really does work and it happens to be a permanent or long-lasting treatment. Cool. That would give us data that looks like this. And maybe that's a good thing, right, about the treatment and how it works. But there's a possibility too here, a second explanation that would give us the same damn data. And that would be maybe some other event happened around the time of our first switch to the B phase. Maybe the participant hit a growth spurt, or maybe they quit cigarettes finally, or maybe they were affected by something in the news, or any of a million other things might have caused this lasting change in behavior. We don't know if it was our treatment or one of those other things. So even with a good solid reversal design, getting data like this ends up ambiguous. If our data looks like this, we don't know if the treatment works. We need some additional information. Basically, reversal designs, they don't work as well, or at least we'll need some methodological tweaks to study treatments that cause lasting or permanent changes. And we'll get into those variations later in the course. But for now, I just kind of want to make the basic logic of a reversal design clear for a simple type of reversal design. So here's another example that might actually, hit home if you got a friend of yours who tries new fads or, loves to give their own anecdotal evidence for things. So for example, maybe your friend is fighting irritable bowel syndrome and they decide to try switching from their generic crappy diet of Hot Pockets and processed foods to what they consider a real food diet, whatever that means to them. Let's say they record their IBS symptoms for a week on their usual crappy diet, and then they record their symptoms after switching to the new real food diet. Here's their data on the left here. That's their data. They certainly have fewer symptoms now. We could probably all agree on that. So you can see why they got all hyped up and want to tell their friends all about the wonders of the real food diet, and they're posting about it on Insta and everything. But they've basically done an A-B design without any reversal. The question is, would this data be convincing? Would you, as a scientist, be convinced by this, that a real food diet is definitely better? Now, it's going to be tempting to say yes, especially since this conclusion fits so comfortably with our preconceived notions, right? Our confirmation bias comes into play here for sure. We want to believe that real food diet works, or maybe we have other reasons we already hold that belief. So this data feels more convincing than it actually is. It's not really that good of evidence. So let's be scientists. Let's think critically here. What else might explain this data? You could pause the video, try and come up with some alternative explanations for the sudden improvement in symptoms on day 8. Now, what if your friend instead did a proper reversal design? Maybe something simple like an AB-AB design. That's better, at least. They measure their symptoms on the crap diet, on the real food diet for a while, then on the crap diet for another week, and then on the real food diet for another week. Based on the data you see here, assuming this is the data they get for their symptoms, should we conclude that the real food diet is better than the generic crap diet? Maybe, but maybe not. It's kind of unclear from this data, right? The first B phase of real food, it had maybe a little decline in symptoms those first couple days, although we saw a day just about as good back in the original baseline. But we also got the worst symptoms of the study on day 10 during the real food diet. So in every phase, there was quite a bit of variation in the symptoms. There's not really a clear or strong pattern here. So I wouldn't run to the presses telling people that this study shows us real food is better than a generic crap diet. Even if I believe that claim already for some other reasons, this isn't good evidence of that. But what if your friend did that AB-AB design and the results looked like this instead? Now we've got a more clear decrease in symptoms over time, right? That's promising. And indeed, it might be that those first 10 days on the real food diet had a lasting impact, and that last week on the real food diet is continuing the improvement. That's possible. That might be what we're seeing here. Or it could be that something else was happening during the month of this whole study that led to the improved symptoms, totally unrelated to diet. For example, the person might have taken up exercise this month. We don't know. Or maybe they moved to a new city where there's less air pollution, and that's what's changing things. Or maybe they were prescribed Lotrinex at the start of this month. Or maybe they even just started taking Tums with every meal. From this data, we can't be very sure that the treatment of real food diet caused these improvements in their IBS, as nice as those changes might be, and as better as their life is at the end of this month. It could be that the changes are unrelated to the real food diet, and in fact, maybe real food diet doesn't work. This data actually can't distinguish those possibilities. Okay? Now, what if the data for your friend looks like this? In this case, it does seem a little more in line with the idea that real food diet truly works, because the symptoms are clearly lower during those phases when they do the real food, and only during those phases. So it's unlikely that a random event or change on day 7 caused this pattern of data. Now, it's still possible, I guess, that there were 3 coincidences, one on day 7, one on day 18, and a different one on day 24, and those other things caused the symptom changes, but that just seems much less likely than when our friend just did an A phase and a B phase with no reversal. So even this simple of a reversal, just AB, has the potential to give us much stronger evidence that the treatment causes changes, at least if our data comes out in a clear pattern like this. And obviously, the more reversals we do, the stronger that conclusion. So with enough reversals, and especially if they're timed somewhat randomly, the only alternative explanation would be if we make some other confounding change every time we do the reversals. Like if the person only takes Tums with their meals during the real food diet phase, but never takes Tums during the crap diet phases. But that seems unlikely, right? So like every research design, it can never give us 100% certainty that our intervention is causing a difference or change. But if we do things carefully and avoid experimental confounds, we can often get pretty strong evidence for causation. For now, I just wanted to introduce the idea of reversal designs because we will see variations or versions of them used in a lot of the studies we'll talk about during this course. So we took care of some of those compounds. Okay, now for the final intro video of the course that'll be coming next, one more sort of warm-up video for the course, I want to address something you may have wondered about during this video. In those previous examples of data I just talked about, I asked you to make some conclusions about whether a change in symptoms had happened simply by looking at the graph, not running stats or anything. And in some cases, like our final one, it was very clear, right? But in the first graph we saw, the one in the bottom left here, it was a lot more subtle and probably felt a lot less clear for you trying to judge if a change had happened. So in this next little video, I'm just going to be introducing the idea of visual analysis of data, how we might judge whether something changed from one phase to another in a reversal design when we're analyzing a single subject's data on its own, rather than averaging across hundreds of people and running statistics to make conclusions about averages of people. So how do we make conclusions about an individual rather than a group summary number? That'll be the next video.